3, nos fuimos. Okay, hi everyone, I think we are live. So I'm Nicolás Bernal from Universidad de Nariño in Bogotá, Colombia. And we are super happy to have today Aurore Courtoy from Instituto de Física in UNAM from Mexico. So Aurore did her PhD at Universidad de Valencia. And then after a couple of postdoc appointments in Pavia and Liège, she decided to move to Mexico, I think because of Peinado. And, and then she started at the University of Guanajuato, then in the staff, and now she's at UNAM. So Aurore, we are super happy to have you here. So we'll talk about phenomenological analysis of the proton structure, impact of some theoretical constraints. So please,
thank you for the invitation. Let me share the screen. Okay, wait, because just 2 seconds. There made me so many tests that now I'm not sure what I'm sharing. Okay. Okay, can I share this one? Okay. Do you see my screen?
Yes, perfectly.
Okay, so thank you very much for the invitation. I'm really glad to participate to this really nice webinars. And now we're all accustomed to this online seminars, so it's pretty cool. So today I will talk about phenomenological analysis of the proton structure, and I will talk about basically what we call PDF, Parton Distribution Functions, and I will tell you a bit about some impacts of some constraints from theory. Okay. So that's it. So so first, what is the question we're gonna ask ourselves about the proton structure? Because I understand that most of the talks you had in those webinars are about new physics and these kind of things. But today we'll talk about the proton structure. So the questions we have to ask ourselves: what are the phenomenal quests we're going to talk about? And I'm basically I took the list that is on the website of the EIC, which is the Electron Ion Collider, that's going to be built in about 20 years at BNL, Brookhaven National Laboratory in the US. And the questions are pretty fundamental, actually, as you can see on the list. So basically, we're going to talk about how do quarks and gluons make up for nearly all the visible matter in the universe, precision of 3D imaging of nucleons, the proton spin puzzle, because we don't really know how to explain the one half of the proton spin, the emergence of hadronic mass, which is a really hot topic right now, quark and gluon confinement, that's the one people always like and stick to, QCD-based diagrams and other things like that, right? And so we'll focus on a few, well, not all of them, but the one that I highlight here in orange are the ones that I think we can access a bit through the study of PDFs, right? So that's going to be what I'm going to talk about. So those highlighted questions can find some partial answers, but hopefully one day hold the answers, but at least hints or partial answers to the study of Parton Distribution Functions that I will call PDFs in the talk, basically. So I will consider here in this talk some theoretical properties of those PDFs to help constrain them, actually. So I'm going to tell you what are the PDFs, what we know about them, and how we can constrain them from those theoretical properties from 2 points of view. The first one is phenomenology, okay? So basically what we call analysis or global analysis, okay? And from a mathematical point of view, what is the origin of some QCD-based constraints? And if you can trace them back from the data. So to do so, I'm going to focus on there are many things we can say about that, but I'm not an expert in everything. So I would say 2 things. I will focus on 2 main progresses we made, recent papers I had with collaborators. So the first one is with students, actually, at UNAM. And it's about the transversity PDF. We're going to talk about some positivity bounds and how it impacts the fit of this PDF. And then the second one is a more recent paper with a collaborator, and how we can fulfill what we call the Coaccounting rules for the unpolarized PDF. And I'm going to explain what they are. Okay. So two cents to the contribution of these questions. Okay, so first I'm going to tell you what's the hadron structure, and we study them. We study it actually, and so we focus on two hadrons, the pion and the proton. So in fact, I said proton. We're going to touch a bit about the pion too. So here's the thing. Pion is quark anti-quark bound states, and the proton is a 3-quark structure here, and they're really interesting, of course. Okay. So why such a mess with and such a big deal with all this hadron structure? Because they are just a bunch of quarks, as people would think. But actually, the real problem with QCD is the degrees of freedom in its evolution, right? So here you see the spectrum of what spectrum? Just a span of Q square. So the resolution of in energy here of the hadron. So it would be a proton because I put a spin. The pion doesn't have any spin. So if you are at really low energy, what you're gonna see basically is a hadron, like just a confined hadron, just 1 degree of freedom is itself here. And in that energy, to what we call mu naught, and and above mu naught too, in that regime here, you would have nonperturbative dynamics, right? And if you go higher in energy, say after from mu naught to mu, and in higher energy, you start seeing almost free, quasi-free Parton degrees of freedom. So in the picture that we have in the middle here, that's what we call the valence quarks. So you would have here the 3 quarks that about that's depicted in the quark model actually, and then you're gonna have two up and 1 down for the proton, and that's the picture we have at mid energy for the proton. But the truth is that the data are basically here, and we have like PQCD in that case, and that's actually what we can see in this diagram here. So this is related to the behavior of the constant here of QCD, right? So alpha strong, and this the behavior of alpha strong, you can see at high energy is really small, so you have perturbative QCD, and at low energy you start having this kind of behavior when it grows, and then you have the confinement happening here. Okay, and that's what you see here: confinement and asymptotic freedom here. And so basically that's the big deal with it, because we wanted to understand the structure, and we need to understand the spectrum here. Okay. Okay, let me see if I can do that here. And so we need to use different tools to understand the hadron structure. And here, as I quote a few things that we can use, the complementarity of tools of QCD analysis. And the main one, of course, is data. And then we have perturbative QCD. And to that, we also have first principle and some model derivative theories. And so, of course, there's a feedback from theory and experiments. And we want to fit it a bit with some phenomenology, some lattice too. So lattice enters into the game. And lattice is first principle. So that's why it doesn't have any other triangle here. So what we're going to try to do in this talk, and what we do in this community, is basically trying to understand QCD from the data using first principle and some feedback from models too, right? So that's the idea. And so how do we do that? So I talk about data, but which kind of data are we talking about here? So I give an example here. That's the same diagram from the IC webpage. And so example of what we call inclusive processes. So in this process, what you can see on the left-hand side here is that you have this electron that emits a photon, and that's going to interact, so collide in that case with a proton, say a proton here in the eye. And so this photon is going to reveal the internal structure of the proton. That's what you can see in the diagram here. And so if you want to put that in a more Feynman-like diagram, which is not really that's the case, you would have this picture here. So that's the electron emits a photon, and it interacts with say a quark, a parton inside the target, and here the target will be here, and we have this blob here, and the blob represents what we don't really know, which is the distribution of this parton inside the target. And you can see in that case, you can have, that's what we call the deep inelastic scattering, DIS. And that's, I think, the most famous, that's the book case of study of hadron structure, so DIS. Okay, and so we're gonna study this. So in that case, you can have the proton that is an unpolarized proton, and you can have an alternately polarized proton here. Okay, and that's what we study for DIS. That was an example of inclusive process, and then we have more processes. Of course, there are many others, right? So I just quote here a few that are related to DIS. So that would be DIS here. And then if you want to make it a bit more complex, we can have semi-inclusive DIS. So in that case, we're gonna see one of the outgoing hadron here, like a pion. And you can have exclusive processes too, like this one here, there's deeply virtual Compton scattering. That's meson production here. And then you can have this some kind of the same thing, but it's exclusive, so you see everything at the end, and you're gonna have this kind of processes. Then of course you can have Drellian, and you can have other kind of processes where those enter. But I just tell you like a few of those because the PDF can have different degrees of freedom too. So you have in that case, I'm gonna tell you we're gonna have like the collinear PDF. Here we can have access to transverse momentum of the quark, and here we can have access to other variables as well. So as you see here, there are some dashed line, and the dashed line represent here what we call factorization theorems, and this allows us to separate what we know from what we don't know. So as I told you before, so this blob here represents the distribution of partons inside the target. And this is a highly non-perturbative object. So in this way, this factorization theorem can separate the non-perturbative object from the perturbative object. And that's how we define, and we can separate so what we can evaluate from PQCD and what we cannot, okay? And basically what we cannot are the blobs here. And that's what I'm trying to tell you in this slide. So that's the same kind of pictures here. But in the case of the inclusive, as I say here, this blob is basically a PDF. So it's a function that depends on X, and I'm going to define in the next slide, and of Q squared. So Q squared here is the resolution. So that's the virtuality of the photon. And in the case of the semi-inclusive processes, we have access to transverse momentum of the quark, of the Parton. And in this case, you have this extra variable here. So it's you have two more dimensions. So X, I'm going to explain, is longitudinal momentum of the quark. In this one, you have longitudinal and transverse momentum as well. Or you can have access to carry-out PDFs, which is what I'm going to talk about here. And in the case of exclusive, you have what you call GPDs. They are generalized Parton distribution functions, and depend on a bunch of more variables here. And as you can see, they need to be paired to this part here, which is in the case of semi-inclusive process, is a fragmentation function. So the quark that is struck by the photon hadronize into a pion, something else, right? And in the case of exclusive processes, it's kind of recombined into a distribution amplitude here. That's the other blob. So you have all these kind of objects. So those are the main objects we can have, and we can access to have this 3D imaging of the proton. And people even talk about 5D imaging, which is a bit more complex, right? So up to here, we have the 3D imaging of the proton. Okay, so now if you want to go into details, so in this talk, I'm gonna focus on only PDFs, collinear PDF. So they will only depend on X, which I'm gonna define very, very soon. And here I give you to what is called leading twist. So it's like we have an expansion on something that is not a coupling constant, but we have an expansion on something different that we call twist, and we stick to the leading, so to the tree level of the PDF expansion, if you like. So to leading order here, we have this definition of the PDF, which is basically it tells you how the quarks are distributed inside the target. So here we just sandwich it in between the proton states, and here we have to take into account the spin because it's a proton in this case. And then you have this tree structure. So you have what you call F1, which is the unpolarized, and I call the ubiquitous unpolarized PDF, because when people talk about PDF, that's the one people refer to usually. And as I just told you, there are many other PDFs, but this is the most famous one. And then we have the helicity PDF, which is the one that is related to the spin distribution of the in this case the quarks, okay. And then we have the transversity PDF. That's the one I'm going to talk about in a few slides. Okay, and so they are defined here on the light cone, that's why we have this n plus. N plus it's the light cone coordinates. And Bjorken X, which is what I just mentioned before, is a kinematic variable that is related, in the case of the definition of PDF here, to the fraction of longitudinal momentum that the active quark carries. So when the quark interacts with the photon or with the probe, it carries a fraction of the momentum of the parent hadron, and this fraction goes from 0 to 1, and that's x, right? And it's related to the variable of Bjorken X. Okay, and as I just said before, this matrix element is related to processes to observable thanks to factorization theorems, to which we connect to the hard part and some other observables too, or other objects too. And then the dependence on Q square on the scale of virtuality of the photon or the probe is given by the de Graaff evolution equations. So this is known. So basically, those PDF depend. So here we didn't put the Q square, but it's supposed to be Q square too. So they depend on X and Q square, and they are interdependent variables. And as I just said, the Q square dependence is known in PQCD, starting from 1 to GV. Of course, there are corrections. There are some corners of kinematics where they have some special corrections that have to be taken into account. But this is basically known from this equation, de Graaff here. And the X dependence is what we don't it's mostly unknown from theory. And so what I would talk about today is this X dependence. How do we define it? How do we find it exactly? How do we extract it from the data? Okay, so that's the state of the art. What that was in June, the state of the art of the PDFs we had, and so you can see an example of these of the unpolarized PDF. So here that's just CT18 next to leading other, but I just quote here a few different groups that work on unpolarized PDFs. The helicity, same, we have different groups here. And just let me point out, it is in Latin America, there's this group here, DSSV. That's with Daniel Florian and Sassot in Argentina. And the transversity, we only have 2 different feeds groups taking care of this transversity PDF, which is one in Pavia, and now we did it in Mexico as well, right? And so I'm going to talk about those 2 PDFs, the unpolarized and transversity PDF in this talk. Okay. So as I said, I'm going to talk about some theoretical constraints on PDFs, and the things that I really want to highlight here is the X dependence on these PDFs, because I said that the Q squared is a bit more under control with PQCD, and so since they are non-perturbative objects, we cannot use PQCD to define them. We can define them to understand this X dependence, and so we have to rely on some first principles or QCD-based constraints that help us to understand this X dependence. And I'm going to give you an example, right, in models and in global analysis. And so what we know about this X dependence is that we need to have positive cross sections. So that's really important because it defines the specific behavior from the PDFs. The support, as I said before, so X has to be between 0 and 1. Okay, so it's the fraction of momentum of that the quarks carry. So it's either it's from nothing to all, but you cannot have less than nothing and more than everything. And the endpoint behavior is also important. So we know that the PDF, when it goes X goes to 1, has to be 0. Okay, that's the important endpoint behavior. And some other QCD-based constraint, like the counting rules that I'm going to talk about. And this is a typical mid-energy QCD-based large X behavior. So I'm going to tell you more in a few slides. But it's a particular picture of QCD that constrain the PDF. And some other manifestation of QCD dynamics. And that's exactly what we want to understand here. Because as I said in the first slide, we want to understand the dynamics of QCD, either confinement, emergence of hadronic mass, and all those things. And all those manifestations of QCD dynamics imply some constraints on the shape of the PDFs. And that's extremely interesting, actually. So let me give you more detailed information about those things. For example, positivity of cross-section, in that case, it implies that the unpolarized PDF has to be positive. And then this implies some other things about about the other PDF. So the helicity must be smaller in absolute value than this unpolarized one, and the transversity obeys this this positivity bound that becomes Sofer bound, and that's extremely interesting here too. And about the endpoint and the counting rules, so both here are like what we call large X behavior, and they constrain and influence the fall off when X goes to 1. So they have to fall off in a certain way, right? And I just quote a few other possible behavior here, like we see here, the emergence of atomic mass, it also controls the broadening of the PDFs when X goes to 1. And if you talk about small X dynamics, and that will control the behavior when X is close to 0. Okay, so these kind of things we can have in PDFs. And so in the second section, I'm in the first now, I'm going to talk about the Sofer bound for the transversity, and in the third section about the Coaccounting rules, okay, and the large X behavior of the PDFs. Something else we have, so I talked about the X dependence, but we also have the X moments that we call the Mellin moments, so the projections on of the PDF on X. And I just got here a few sum rules that are here for the unpolarized case, and they're extremely important sum rules. So they're really sum rules, so those ones don't depend on Q square, they value at all energies, what they call the valence sum rule. So when you integrate from 0 to 1, the PDF, the unpolarized PDF, so say the U quark PDF, then you should obtain the number of U quark that you have, okay? Valence, sorry, so say U valence, you would have 2 U valence, right? And if you integrate this D valence, you would have 1, right? And the momentum sum rule too, so if you sum over all the partons in your proton, and you take the fraction of momentum that you would have for each contribution of the PDF, of each flavor, say, it must sum to 1, okay? That sounds like pretty reasonable. And those sum will constrain the integral and the projections of the integral. So they're also extremely important constraints on the PDFs. Let me give you an example now with a model. Okay, so that's not for the proton, for the pion, because it was a simpler example. Okay, so here you can see on this plot on the right hand side the pion PDF. So the points are extractions of data, so they're not really data. And what you can see the 2 curves, so you have one in black that is what we call a leading order, and then one is next to leading order. It's basically a PDF evaluated in the model, the numbers in the model, and evolved to the scale of the data. Okay, just to give you an idea. And we have to check this list here. Does the model comply all those constraints? And we can see that it's positive. We have the correct support. So we don't really see it because of the scale, but it goes exactly as it should. Okay, and it broadens with the emergence of hadronic mass. That's really cool. And we also have the valence sum rule without any problem. And we have some problems with momentum sum rules and endpoints. And this is related to the Q square evolution. Okay, and there are many other problems and shortcomings like counting rules and other things, right? But just to give you an example of what we can have and achieve in models. And of course, there are many other models, but that's a kind of checklist that we have to do when we have an evaluation of PDFs. Okay, and then if we don't have those ones, we have to explain why, right? So we know exactly why in this model what is missing and what we have, and why this checklist is partially checked. Okay, and now if you we're gonna go to global analysis, and in that case we better have all the most important ones and understand why we don't have the other ones. Okay. Okay. Just to give you an example now of the unpolarized PDF, like real proton unpolarized PDF from global analysis. So that's the one from CT18, and we just talked about the constraints here, and not the game in the model analysis is error treatment. So in that case, they have large data sets, and they also have a lot of theoretical errors that they can afford to really care about because they have many data. And also there's an error coming from parameterization. So what I show here on the right-hand side is a plot. So that's the ratio of PDFs. So the blue band is actually the ratio of, so you will see the error band divided by the central value, okay? The central fit, that will be in 1. So that's for the up quark, and that's for the gluon here. And what you can show also is the the error coming. So if you use a different parametric form, you would have different good fit too, right? And what you can see on both plots is that small and large X region, the small here and the large X regions are the ones that have the largest error still, right? Because there are not so many data in those regions. And so in the case of the unparsed PDF, they have a high degree of sophistication in the analysis here, because they can afford, thanks to the great and large data set they have. And still, I wanted to show you this because it's really important that people understand that even if it's really well known, it's the best known PDF, but you can see you either have an envelope or a central value and an error. So they come with an error, okay? So it should always be quoted with some errors, right? And as I said before, especially at small and large X. Okay, so this is the PDF kinematics that we have for the tree leading to this PDF. So as you can see here, I said large data sets. So that's for the unpolarized one here. And also you can see what is predicted for the EIC. That was the LHEC, but I think it's not going to be made after all. And that's for what you're going to have here for the helicity, and that's future for the EIC. And that's the transversity that I'm going to talk about. As you can see, we can still count exactly the number of points we have, but the EIC is going to help us fix that, and we're going to have more data in about 20 years. But okay, and JLab 12 also is going to fix that a bit. Okay, so you can see the difference between the three PDFs. So this one is a huge data sets, this one average, and this one like tiny data sets. Okay, and that's why we don't know them at the same precision. Okay, so note that I just told you about that. I'm going to talk about transversity PDF, and this work has been done with students. When Jorge is in Peru, but he was at UNAM before, and Rodolfo is about to graduate in Mexico City at UNAM too. Okay, so this transversity PDF, as I just told you, is the least known of the three leading to PDFs. And if you want to represent it, so if you see on this picture here, and if you take this, so you see on the other side. So that would be the motion of the target of the proton, and it is transversely polarized with respect to this direction of motion. And so what it tells you basically, that the naive picture is what is the distribution of quarks that are whose polarization is parallel to that of the hadron, minus anti-parallel to that of the hadron. Okay. And that's what we call transversity. And what we know about this transversity is that it has the support between 0 and 1 for X, the endpoint behavior, as I said before. In that case, we know it has to be 0 at X equal to 0 and 1. And we have this positivity bound that we call the software bound that tells you this constraint here. So this constraints by the other two PDFs, okay? And some characteristic of this transversity PDF is that it requires a semi-inclusive process because it's chiral odd. So it has to partner to another chiral odd quantity, not object, because you ideally want to have a chiral even cross-section. Okay, that's going to be better. And there's no concerning sum rule in that case. It's even more than that. The sum rule here gives us the tensor charge that is probably the only way we can get access from phenomenology to this tensor charge. Okay. So it's something that is like an output of the fit and not an input to it. So that's pretty cool, but it leaves with less constraints for this PDF. Okay, so how do we have access to this transversity PDF? As I said, it has to be semi-inclusive. And so here you can have this quark that hadronizes into a pion, or as I say in the text here, or two pions, right? So there are two different approaches. So it needs to have a fragmentation function in the case of semi-inclusive DIS. There are the processes, but here I focus only in semi-inclusive DIS. And you have the PDF multiplied in the cross-section. Or in the case of most experiments, we have going to be asymmetries, okay? And to another chiral fragmentation function. And there are two different approaches. The first one is what we call the transverse momentum one. In that case, you would have a TMD PDF and TMD fragmentation function, or the collinear one, okay? And as you can see here, I've worked more in collinear and not in TMD. And so the question is actually, how can we do that? Because we have two objects that we need in one observable here. And actually, there are the observables that give us access to this fragmentation function part. that are basically E plus E minus at Bell, okay? And they gave us access to both single hadron and dihedron. So dihedron is the one that give us the collinear access. And I just show you here the plots for this collinear here. So we can have access to this ratio of Carroll's fermentation function divided by a nonpolarized one. So and then we plug that into, properly plug that into the asymmetries, and we get access to this transversity PDF. That's what we do, okay? And so now that we have all these observables well defined, there comes the fitting thing. So how do we do this analysis? So we have to define a function of x, right? That's what we want to get from the data, this function of x. And then I'm not talking about Q square because it's already taken into account in the evolution by DGLAP, okay? This is going consistently here in those papers. And so we have to choose a functional form. And so the first step to do, and that's actually the first thing, the natural thing to do is to impose the positivity bound in a certain way. And as you can see, this positivity bound, they depend on the expression of the other two PDFs, okay? So it comes with an error here that is not quantified, it comes with an error. And so the most natural way, that's what we did it in the first time, is to express this PDF as a function that goes from -1 to 1, okay, times the expression of this upper bound, okay? And that's what we've done here, and you can see that would be the bound in blue here. And then we have two different, so the green and the red are both extractions of the Pavia group. They're slightly different. And then you can see there's a clear saturation in this case that I show here to the functional form we use, but we have saturation of the bound in some particular region here. So that's for the U balance, and that's for the D balance, okay? And so, and there's another more recent feat here by my colleagues in Pavia. That's what I call Pavia 18. Okay, so that's pretty cool. That's wonderful. But there's room for improvement, like in many cases. And so the data we have, so they come from basically they came at that time from Hermes and Compass. So Compass is SPS. So if you wonder if the SPS is still working, yes, the SPS is still giving us a lot of information about hadron structure. And you can see here, so we have proton data and deuteron data. And as you can see here, there are some of the points. So those are extractions from the, so they are not data, right? Because I give you the PDF here. So we pre-extracted them, so we pre-cooked them with a fermentation function part. And you can see that some of the points give us a hard time with the positivity bounds, okay? And there's another thing that's also really interesting and important too, is that once we integrate this function here, as I said, so the first Mellin moment give us access to what we call the tensor charge. And if we compare it with the lattice evaluation, so all those one will be lattice, okay? And then we have different phenomenological extraction, you would see that this it tends to be in disagreement with the lattice. So we want to understand what's going on, okay? So I don't claim there's a disagreement, I just say it tends to not to agree completely, okay? There's some tension, okay? So that's why we did something different in Mexico. And so we decided to make a second step, and we implicitly imposed the bounds of large X. And so we just constrain the PDF through the fitting procedure. So that's slightly different. And we just make 3 steps instead of 1 step, and we have like more flexibility. So the first thing is that we realize there's some tension between what we have, the data we have, okay, and the positivity bound. So the first thing we did is to evaluate the probability of this bound given the data, and then we weight the objective function here with this probability. So that gives us like more freedom actually for the fit. The second thing we did is that, so we have to parameterize the X dependence. So we take here we take the Bernstein polynomials. That's what we like those ones in particular. You can see here the functional forms, and we repeat n times the fits. That's what we call the bootstrap method. And then at the end, what we have to do, we still have to constrain some kind of physical fall-off, because we want the PDF to go to 0 when X goes to 1. And what we can do if we don't impose this by this software bound here by hand, well, or in the functional form, we have to impose it in a different way. So the way we impose that is that we force it with the Lagrange multiplier technique. As you can see, that's an example that the students gave me. So that's So in the red inside, not the bound, this red will be the first iteration of the fit we have. And as you can see, the down quark tends to go a bit widely below the bound. So it's not approved by, it's kind of forbidden by the bound. And so what we do is that we impose in 2 different points that it has to be reduced, right? And so we impose it by the Lagrange multiplier. And as you can see, it comes back inside the bound here and here. Okay, that's what I want to show you here. That was pretty cool to play with that. And so that's the result, right? So we have here that we see the result for the U valence at 1 and 2 sigma, and for the D valence. And as you can see, we still allowed to kind of go above and below the bound, because we realized that there was room for that. The data would allow that, right? And so we compare here on the right hand side the Pavia 18 and the Mexico 19 extractions, and you can see there's a huge difference for the D valence. And actually, the fact that we relax a bit the bound in agreement with the data, we see that there's more flexibility for the X dependence. So that's pretty cool. There's a balance interplay between the constraints from first principles and the data. Okay, and that was what we did. And why is it important? Actually, yes, people will say, what do we care about transversity? And then actually, well, first it's one of the 3 leading to SPDF of the proton, so that's pretty important. But also now it can be compared with the lattice, and it will give us what I could say the tensor charge, and I will say a bit more next slide. So so now the great thing is that lattice is doing a lot of progresses, and we can see that they have what they call as quasi pseudo PDFs, and they also have the melting moments. So if you see that would be the kind of flag-like, they're not really the flag. In this reference, you can see the tables in which you have the average, or in that case, not average because it's so huge. They are so huge that there's no possible average. So far, it will change in the future, I guess. This kind of flag-like average between the lattice and phenomenology. Okay, so in this case, you have all the lattice results and you have all the pheno results up to that date. Okay, that's changed since then. And then what you can see is that there's a slight, as I said before, discrepancy between those things. And then you can see the kind of average for this GT here. In Mexico here, 19 is quoted here, so that's pretty important. And you can also compare now the quasi-pseudo PDFs from lattice and phenomenology. And you can see phenomenology still has a lot of uncertainty. So we have the cyan one, and then the other one is this pink, orangey pink, and so jam would be this purple one here, and the lattice have the tiny error bands, right? So this is really interesting to compare with them. So that's pretty cool. And so going back to this tensor charge, it's still an open question, right? So that's pretty important here. So I just added my point, sorry, here, because you don't see when I point from the screen. And you can see that we can find agreement with the lattice for this isovector combination. But then when we go to this, so there will be the U, so the delta U here, so that the U valence for the tensor charge and the D valence for the tensor charge here. So we compare phenomenology with lattice, and you can see there's a huge discrepancy, especially for the U quark, right? So that's what that is Pavia 18, that is Mexico 19, and then some people here from this JAM 20, they find something that is kind of in agreement with the lattice, this ellipse here. Okay, and so what is interesting now is that they did the same exercise for the EIC. So they used the pseudo data for the EIC. Okay, and what they found. So if I just zoom inside this ellipse here, so that will be the same pink ellipse here, different scale, and that would be the impact on the from the EIC on the error band. So you would see it would be really reduced, right? So there will be a huge reduction of the error bands, and that will be then comparable with lattice, right? So we could say in the future if there's discrepancy or not, right? Of course, there will be a lot of progress in different things, but okay, that's a good hope for us. And so why is it so important? And actually, GT is relevant for searches for physics beyond the standard model. So that's pretty interesting too. Okay, and that's the team for the Mexican transversity. Okay. So that was for the transversity. Let me just go now to another topic, which is the Coaccounting rules. Let me see if I still have time. Yes. Okay. And this was done with my colleague Pavel Nadolski from SMU in Texas, in Dallas, Texas. And so that's also related to the QCD-based behavior or constraints we have for PDFs. So that's in the same line. So before we had this positively bound constraint from the constraining the transversity PDF, and now we want to see what can we hint from this QCD-based large X behavior of the Coaccounting rules. So the Coaccounting rules, they are from they were expressed in the 70s. So you can see a lot of references here, and they're pretty interesting. So they tell you what's supposed to be the behavior of processes. So say in the threshold limit for DIS. So in that case, you would have when X goes to 1 in DIS, you would have the structure function here. So F2, so DIS can be expressed in terms of F2 structure functions here. They are the observables. And what they tell you is what is the behavior of the structure functions here, so the observables for DIS, when X goes to 1, so close to threshold. Okay, and basically the proofs for this behavior invokes almost unperturbed targets and a weak coupling, right? And what it tells you is that you should expect this behavior of y minus x. Here I put x Bjorken because of it's the observable, y minus x to some power, and this power basically is equal to the number of spectators, to the quarks, and some helicities of the quark and the target. So if I want to express this behavior and I want to extend it to PDFs, which I'm going to tell you after that, which will not really be done, but okay. If I want to extend that to PDFs, it's usually understood as this the following. So the PDF, the unpolarized PDF, when X goes to 1, it's expected to behave like 1 minus X to the power 3 for the proton here, for the valence quarks. So that will be this diagram here. So if I have an active quark here that is the valence quark, then I should expect this PDF to behave like a minus X to the power 3 when X goes to 1. And for the gluon, I have different contributions, but one of those contributions would be 1 minus X to the power larger than 4, and the C larger than 5. Okay, and that's what we wanted to check here for the unpolarized PDFs. So why is it so interesting? Because as I say, the picture that was invoked in the proofs of those Coaccounting for processes is a picture that is more like in this regime actually, and so it's not the first principle, but it is it's really well let's say well it's really based on the QCD picture. And as we talk about QCD pictures, we want to see if we can understand and link the QCD pictures we have at low energy and high energy. So that's the same diagram that I showed in the third slide. And as you can see, when we are at hadronic scale, that's a mu naught, that's the famous mu naught I had before, that is smaller than 1 GeV squared. We have a prefactorized pictures, and we have, as I said before, non-perturbative dynamics here. So that's where we're going to have all the things that are, from my point of view, all the interesting things that we have inside. The hadrons happening, confinement, and we have chiral symmetry, and all those kind of things that happen in here. But of course, we can. The idea is, can we trace them back? So the thing that we can see them happening here, that's why we have the most impact here. But the question is, can we trace them back from the data here? So we know the data are in PQCD. We have quasi-free Partoning degrees of freedom that define some scheme, and of course there are corrections coming from PQCD as well. But the data are mainly here. So the question is, can we trace back what's happening at low energy, these manifestations of dynamics of QCD? Can we trace them back at high energy, right? And to answer this question, we first need to bridge, to link them, right? And so when we want to link that, so we need to link the non-perturbative and perturbative approaches and go through this mid-range energy. And that's where we have the Coaccounting rules. So that's pretty interesting. And so the question is, do we observe these so QCRs are Coaccounting rules in data described by PQCD? And so we want to narrow that question, because that's like a really broad and vague question. And if we want to narrow, we want to ask the question, do we find clear evidence or some hints, right? So so hints, we know, we all know how to do that. We just want to check if there's an agreement of the model. So model can be, say, a global analysis output, like theoretical model for that, or a model like a non-perturbative model, like NGL that I showed before. So do we find agreement of the model with the data? And so we know how to do that. We can evaluate like a chi-square, something else. And also, of course, we need uncertainties to be quoted to provide a faithful conclusion to that, right? But this is what we do almost every day. We just check with the data if we are close to the data with some range, and that's a hint that it works. But it's not an evidence, okay? So that's different. So here, as I said before, the Coaccounting rules, they give us a specific polynomial form. So we want to check a y minus x behavior, right? So that's not exactly the same as just checking against the data, right? And so the problem here is that we have this polynomial form, and there's more than one possible solution to the choice of functional form when we compare with the data, right? And so we want to ask the question now is, how do we test some specific x shapes? Okay, so there are different things to take into account here. I give an example of two things that are related. So first is that we're talking about large x, right? So what is large x? So in Pheno, we talk about x from 0.6 to 0.9 because we almost never go to 1. And in theory, it's x goes to 1. That's the limit goes to 1. So there will be a difference between what we call the global and local degrees of the polynomial here. And I illustrate that in that plot here. So if you take that range that I just mentioned, and if you want, so globally, we have this this orange curve that is y minus x, and it's y minus x, and you see globally, it agrees with this blue curve, and the blue curve is actually a sum of higher degrees polynomial, right? And so globally, they would agree, but if you go to x goes to 1, here, they won't agree, right? So the global agreement would be okay, but not the local one, right? And this has to do too with what we call polynomial mimicry, which is a mathematical equivalence of polynomial of different orders. And I'm going to talk about that in the next slide. And so, so we can find all the information in that paper. It's really interesting. So if you want to have a look, I will invite you to read it. So an example of this polynomial mimicry is given by the Bezier curve. Okay, and the Bezier curve they're defined on Birch and polynomial basis. I think you've realized by now that we like the Birch polynomials here. Okay, so just an example here. So we have here the second degree polynomial here that gives you this cyan curve. And I can also, with a clever choice of B prime and B second, reproduce this curve, the cyan curve, by a third degree polynomial, right? So that's an example of how you can increase or decrease the polynomial degree here. And those Bezier curves can also be used to interpolate polynomials. And that's really interesting when we think about this ideal example. If we have data, so say we have data, ideal case, that's never gonna happen. We have data with no errors, and they are spaced equally, wonderful, and in a really clever way, right? Which is never gonna happen. Okay, and say we have those data here. So here it's kind of it's like a trick because the data I took them from we took them from this form here, which is 30x squared 1 minus x squared, and so we know in that case for this example we knew the distribution, this x behavior, the parametric behavior of the data. Okay, so now say there are data we don't know the behavior and we want to interpolate to the data. Can we reproduce the original function, right? And so we can do that, and there's something interesting that is not exactly expressed here in this plot. If the degree of the polynomial is equal to the number of points minus 1, then there's a unique solution, right? So there's a closed form solution to the problem, and we can use this thing here. And what is also interesting, so in that case, the case I show here, actually it's a simple case, so we can afford to go to 9 points. And what is really interesting is that this interpolation through Bezier curve allows an expansion in y minus x about x equal 1, right? That's what we want to see here. So what I show by the dashed curves here is the truncated expansion of this monomial expansion here, okay? So what you can see is that there's no term that goes like y minus x to the power 0, 1, okay, as expected. And the first one is actually the number 2. So that's the sum of 0, 0, and this 2, and 3 and 4, right? So we can reproduce perfectly in that case the data, and we can reproduce the initial function here. But it gets more tricky when we have a complex functional form, which could happen in global analysis or in models too. So the question is, can we pin down the large X behavior, right? So if we have a complex form, because of course the PDFs can be really complex. So in that case, you can see here, that's an example. Okay, so we know that we have the points here. We have points coming from this function, okay? Of course, in the real case, we won't know the function. We have to guess the function, okay? And you have this 1 minus x to the power 2 here, and x2, and another function, okay? And this function can, of course, affect the large X behavior, but ideally not too much, right? And so we made the same example here, but so in that case, we have, we want to reproduce here with the Bezier curve of the 8th degree with 9 points. So in that case, there's a closed form solution. And so we take 3 different sampling of the data coming from this one here. And what you can see, so here they're more spaced, less spaced, and no large X, and finely spaced here, but only at large X, right? And so what you can see is that they have 3 different behavior. They interpolate pretty well. They extrapolate really badly here, especially. But what you can see is that, have a look at the truncated sum, right? So we want to check exactly what's going on. And what you can see first is that in the 3 cases, you have n equal 1 truncation. So we have a 1 minus x to the power 1, which is not present here, right? And it changes a lot depending on the spacing, sampling of the data, right? And so you can see that there's also different behavior of the highest power, and that they are non-negligible too. So you have n equal to 2 that comes here, but all those terms here could also have an influence here. So what you can see is that the sampling of the data give us a spurious contribution of n equal to 1, okay? And we also have a lot of different powers that are non-negligible, like n3 to 8, right? And all those terms are sources of uncertainties. So even if you don't have errors in the data, we're going to have an uncertainty in reproducing this y minus x behavior, right? So that's pretty interesting. And what it tells us is that we cannot really pin down this large X behavior unless maybe we're going to have extremely large X data at some point, right? And so can we reconstruct this original function and find a meaningful expansion here? No, there's no clear evidence of Coaccounting rules. So in that case, we cannot claim that we find a y minus x behavior here, this specific shape of the PDF. Okay, so the question is, can we still find hints of Coaccounting rules? And so we want to check here in the case of CT18. So we want to see if there's agreement of model with data testing for the structure function here, so F2, in the global fields of CT18 and next to leading other. So that would be the expression here for the structure function that you have. And that's where the PDF comes into play, right? And the PDF is given like this functional form. As you can see, there's x to the power a1, y minus x to the power a2, and that's the 1 minus x behavior that we want to check here, right? And it comes multiplied by a function that, guess what, is Gaussian polynomials. Okay, and that's the CT18 fit, okay? And so to check the large X behavior here in this exponent, we defined an effective exponent in this way. So this A2 effective will give us this A2 slightly modified by this function here. And so we checked that A2 effective for different values of X. That's what I call the Pheno interval of large X, and for a different value of Q. As you can see there, so here we have Q equal to 2 GV, 4 GV, 10 GVs. And what we expect, remember the few slides before, we expect to find 3 from the Coaccounting rules. And what we find here is that we kind of find an extremely large X. And within uncertainties, we kind of find this exponent of 3, right? So within uncertainties. So it's okay for the observable structure function here. So the question is, can we find the same thing for the PDF? So that's the structure function here. As you can see, it comes with a more complex structure here. And now we have the PDF, okay? And so we want to check the PDF. And so that's what we do here. So the PDF for CT18 next to the other, and we repeat they repeated the fits for n equal 300, right? And I played with them, right? Okay. And so what we see is that, say here, you have the A2 for effective for U valence and for D valence. And what you expect for the Coaccounting rules is what you have in the cross here. So that what we have in the tabulated CT18 paper. And if we check here the Hessian propagation of the A2 effective of CT18, it gives this ellipse here, right? And if you play with all the parameterization that are a bit relaxed, you would find this scatter plot here. Okay, so you still agree with the Coaccounting rules more or less at the given scale. You can do the same thing with the gluon and some C combination. And what you can see here in the case of CT18 is that the gluon is a bit too small with respect to what you expect for Coaccounting rules, okay? And another thing that is pretty interesting is that, of course, it has to run with PQCD, and so that would be the same scatter plot here. And if I change the value of Q here, go to 4 and 10 GeV, I see a clear running with PQCD. So the question here, to make it short, is that we don't see universality of Coaccounting rules, and there's a dependence on the flavor here and on the process, that I haven't shown that here. Okay, so now, why is that so important? As I said before, we want to check some manifestations of QCD at low energy in the data at high energy, right? And so that's why we want to link the two and to bridge them, kind of. And so let me just go back to the pion, because it's a clear example. So now is can we disentangle this low energy manifestation in the PDFs? And so I talked about the images of hadronic mass, and it's pretty hot topic for the pion and the proton too. But the pion is it might be easier to visualize because it comes from chiral symmetry breaking, right? And that's pretty cool. And so here that's the same plot as before, right? So that was, as I said, that would be the NGL behavior of the PDF. And in that case, we have chiral symmetry breaking. So we have this broadening of the PDF. So you can see here that it's pretty broad, and we have to compare that some scale to this y minus x to the power 2 in the case of the pion behavior, right? So you see here. And so the question that we have to ask ourselves in the future is, can we disentangle those two behaviors? Say we have this broadened PDF at mu naught, and we have the Coaccounting rules that give us this tail at mid Q square values. And then we're going to have data. So those are extraction of the data, they're not really data, right? But it's a beautiful picture to have in mind. And so what we see is that we have concurrent effects. And so the question is, can we distinguish between and recognize those two effects at the scale of the data mu square, right? And that's a tricky question, right? Why? Because I explained a few slides before that we have this mimicry, Polynomial mimicry. We have process dependence on here in the case of Coaccounting rules, and then we're going to have QCD corrections and all those things. And all those shortcomings, or well, the real physics actually, they explain why we find powers of y minus x that was like 1 or that are higher than 2 in global analysis. But they also take into account the change of degrees of freedom if in some non-perturbative approaches, right? Because a quark at low energy is not a quark at high energy. It's not the same definition, of course. So we have to connect those two things together. And so that was pretty interesting. So if you really want to understand, please read the paper. Can we validate some manifestation of QCD? And so what we suggest is that we need to open strategies to discriminate some parameterization, right? So for example, can we have data with really large X where we don't have that much hadronic activity? That's an example, right? So we want to connect this low and high energy PDFs. Okay, so I think that, yeah, on time. Conclusions, sorry. So I tried to address how several first principles or QCD-based constraints govern the shape of PDFs, okay? And this helps us to guide the community towards the understanding of some key questions about the hadron structure. So quick questions, I just put 3 here, but there were more on the first slides. So we have this precision 3D imaging of nucleons, the emergence of hadronic mass, and basically how quark and gluons make up for all this visible matter, so the matter of the universe. And I just touched 2 specific points. And as I said, it's my two cents to the community, the recent 2 cents contribution, which is in the first case the transitive PDF. So we have seen that we can associate to it some faithful uncertainties coming from the data. Okay. And how do we do that? We make this thorough analysis of combining the data and first principle. So we just don't impose the first principle. We try to be more flexible with them. Okay, as much as the data let us do, of course, right? And in the second case, we analyze large X PDF, and we try to understand what are the conditions to understand from these primordial PDFs from scattering data. And it was, in my point of view, a very interesting step towards bridging non-perturbative and perturbative pictures. And what is extremely important in those conclusions is that there's a huge role played by the uncertainties of coming from the data. Okay, thank you.
Thank you very much, Aurore, for this super nice talk. So are there questions or comments from the audience? Well, I have one, so maybe I can start. So yes. Like a couple of slides ago, you mentioned that you found no universality of the quark counting rules. Mm-hmm. So I got kind of confused. Were you expecting that? Were you expecting universality, or what was exactly your point?
Okay. So let me go back. Maybe it was here. Okay.
Exactly. Yes.
Okay, so in all the talk, I used two different terms: so first principle and QCD-based constraints, right? But usually these Coaccounting rules have been used like first principles. So people have considered them as first principles because probably when they were proposed, they were really strong, right? So it was a really strong constraint, and it was really well motivated. And of course, it was in the 70s. So what we wanted to do now is to see if they were so strongly motivated. And they are in some sense, how to say, here, as you can see here, for the total function here. So for observables, for this one in particular, it's motivated, right? So now if you extend that to modern PDFs, it's not so strongly motivated. That's why I don't call it first principle. So the conclusion is that it's not really first principle. It's a QCD-based picture. So yes, it's not. We don't observe it. We did not really expect in that case really precise universality. Yes.
Okay. Thanks. More questions or comments?
So I remember a long time ago that when one wanted to build, for example, the neutron electric dipole moment, starting from the quarks, you could do that with counting rules. I remember there was this neutron model. There were other alternatives, I remember, to that. In what way do you think that your work will feed onto this? Like, if we ever observe a neutron EDM, would that? How do you think that would give us information about individual quark CDMs coming from this? Do you think it would be possible to get some information?
Okay, that's interesting. So I don't exactly remember how it goes. So in the EDMs, it would expect to have some charge, right? So I think you can have some charge coming from the PDFs. So is it related to the PDF? So I don't remember exactly how you can express in terms of PDFs.
No, it wasn't. It wasn't. I don't remember much either.
So maybe it was another counting rule. So maybe it was another counting rule, right? I don't know. Okay, we would have to have a look. Yes, but if it's related to the PDFs, so I thought it was related more to the mailing moments of the PDFs, because you can have an impact on DDM coming from the charges. So I don't know exactly in that case. So
okay, I don't know the connection. It was a long time ago, so I've forgotten most of the details.
Yes, and then counting rule can be used for different things, right? So those quark counting rules are for this large X behavior. But if it is
I see. Okay.
behavior, yeah.
Okay. At some point, when you commented on the connection between large X and low X, I thought that you could actually say some things about this sort of models for, say, the neutron EDMs. But okay, maybe probably I misunderstood.
No, it could be. I don't know. I need to see what you're thinking about. So maybe we can discuss later. But basically, if it comes from the PDF, so we're gonna have like analysis of the PDFs, and what you're gonna find here for this A2 can have an impact on some of the things, probably. Yes. So the large X PDF will change, right? So I don't exactly know in the case of DDM or it plugs into that. But okay, we can have a look if you want.
Would be interesting.
Yes.
Thanks.
Any further questions?
Can I ask a question?
Yeah. For me, it's okay.
So at somewhere near the beginning, you mentioned beyond the standard model physics.
Yes.
And I would like to comment on that. A specific kind of beyond standard model physics is, I don't know if you are familiar with the standard model extension. This is a model in which you pose Lorentz or CPT tiny violations.
Mm-hmm.
So my question is that if you are aware whether these your findings could be used in that context to improve bounds on the QCD sector, which I understand are harder to impose that, for example, in the QED sector. I don't know if you're familiar with that.
Okay, no. Okay. So I remember that some colleagues, actually with the dihedron part, so some colleagues had a look at CP violating observables related to this. Okay, let me go back. So where are dihedron? Okay, so here, okay, let me just go here. So in this kind of observable here, you can define this fermentation function here, but you can, so this fermentation function here, this one is Kyle out, right? And you can define other ones that if you relax. So the way we build them, we construct this, we constrain actually the PDFs, and the fermentation function is through where we define Lorentz scalars. But you can also define different things. So there was one of those observable, objects could be related to some CP violating observable. I don't remember now, but I can send you. It was in the proceeding. But that would be the things we have. But basically, in hadron structure, the way you define them, you impose, of course, all the symmetries that you think must be respected, right? So you fulfill Lorentz symmetry, you fulfill all of those things. Yes. So in that case, I don't really know if they can. So they could be extended to search for other kind of non-fulfilling symmetries. But I think it's more tricky, right? So what I refer to here in this case for the BSM was actually related to the Dirac bilinear. So okay, here. So here, as you can see, that's a tensor charge, which means tensor interaction, right? So tensor here, it's defined in the hadronic sense. We can have a tensor as I showed before. So here you have sigma mu nu, right? And in those papers, it's basically in the case of beta decay, you would have so this tensor charge can be related to the leptonic part that would be tensor, right? And here this one is for EDM actually, right? So this the third one is the tensor interaction, tensor charge here for the EDM. So that's more about those ones here that I quote are more about finding other kind of interactions.
Okay, thank you very much.
Any further questions to Aurore?
I have a very, kind of naive question in that aspect, in the sense, how does this analysis improve, for instance, this Monte Carlo code like Pythia or Herwig that they use, in some sense, the PDF for the hadronization and other stuff that occurs higher scale in hadronic physics?
Okay, so
I mean, in the sense that if there is a strong feedback between these Monte Carlo communities and what they are presenting, indeed.
From what I understand, they don't use PDFs, right? So they use some different models for generating the Monte Carlo, right? So they would use, for example, I don't remember which one is what. So they would use different things. So for example, in the case of hadronization, they would use like a string model, like a string tension model, and another one would use different models. So they are not really based on PDFs. They will give you events, right? So the events based on particular not modeling, but concepts of how the Parton showers are made, for example. So they are more like I don't think there's really a feedback coming from them, but I'm not sure. So I might be saying that is something that is wrong. Yeah.
No, yeah. I was thinking because, for instance, in PIPIA, that indeed, as you said, they use the string model.
Mm-hmm.
I mean, okay, of course, you have all the Monte Carlo of the production of the event, but usually if you want to simulate some kind of event of proton-proton collision, they have some input to generate then the initial, like the seeds from them.
Okay.
They produce the other hadrons, for instance.
Okay, so if you want to have something like more complete, so you have that, you have the PDFs. Yes, I don't know why it's always plugged into that. Yes, that's a good thing, a good question. Yeah, I don't know. Yeah, sorry.
No worry.
Okay, it was me. Sorry. More questions?
So you mentioned this electron-ion collider.
Yes.
And how you could get information from the unpolarized PDF coming from the observation only of the electrons scattering, right?
Yes.
And then depending on what else you were seeing, you would get other information. But can you get also interesting information if you don't see the electron? That means if you have an interaction via a W, such that it transforms into a...
Yeah, okay. Okay, let me go back there. And actually, what I quoted is DIS is not only in DIC, it's everywhere where you have DIS. So that would be DIS. Okay, so it's EIC and other experiments as well, right? Yeah, of course. So here the dominant will be the gamma, but you can have the Z, you can have the W, but it won't be it won't be a dominant one. Yes, but you can have that too. Yes.
Sure, but then that has got a chiral structure. I mean, that will probe the chiral structure of the...
That would change. So that would change exactly what I show here. That would change all that, right? You're not going to have the same structure here.
Right.
They won't be the same.
Or
they can be different combination of those ones, but they're so you have to redo all the thing. So here it's based on the fact that you do have this electromagnetic coupling here, and the way you decompose that, yes, it changes a bit, yes.
Right, but I guess there will be interplay between what you see on the gamma side and what you get from the W side, or from the Z side that you have
mentioned. They will be, yes. So some of them will be okay. Yes, okay. So some yes, so we have this one, but what will happen is that you can define different sort of function here. So what will change is will be the charges we're gonna have, right? And the way they are combined is different too. So the structure function will be different.
They would be different.
The structure function will be different, and the PDF. No, maybe the PDF will be the same. Wait, let me think. Okay, the way you're gonna plug this thing into that's gonna be different for sure. Yes, because we're gonna have the same coupling. So the full observable is gonna be different.
Right. So you wouldn't get any useful information for your transverse PDF by interactions via W's.
I'm not saying it's not useful, but I'm not. What I'm saying is that it might not. It might not be really well. I think it's going to be much more suppressed than this one. So
yeah.
So in that case, you're gonna have the gamma, and then you can have the z, and it's gonna be tiny, right? And actually, JLab they checked that for PVDIS. So if you want to have a look at PVDIS, but that's for the unpolarized case, right? And so of course it's the dominant one would be the gamma always in that case.
Yeah, for sure. I was actually thinking that I wouldn't know how to disentangle the gamma and the Z contribution. I mean, in principle, you
can with the charges. Okay, you can have a look at the PVDIS papers, because the way it connects is different. So here you're gonna have the electric charge, right? And so it's gonna change the way you combine the charges, and you can have this interference term, and that's how you can. Well, I'm not saying it's not tricky, but it has been done. Actually, you can check all this, the thing that Jefferson lab for the PVDIS. That's exactly what they were looking at.
Okay, great. Okay, thank you.
Excellent. Maybe a last question for Aurore?
Yeah, I have a very, I have another question for Aurore. Because I guess in some part you call it, but I don't, the question is if there is any, how to improve, for instance, to find a small difference between proton and antiproton with this analysis. I mean, because you start with some set of rules like positivity and other kind of nice behavior that they should have function, but is this criterion must be like symmetrical for particle antiparticle, or do you expect that using this kind of tool also with enough statistic to start to see differences between proton antiprotons? I mean, this tiny,
like you would see like for example U and U bar. Yes, I think you can. I'm not an expert in those things, but I guess I think it depends on the symmetries you impose in the fitting functions, right? So I don't exactly know which one they impose. That's a question for the colleagues. Should ask. Yes.
Okay.
But you can choose the functional forms and the flavors to respect and fulfill some of the symmetries.
Oh, right.
Sorry, just to comment a little bit. Precisely, that's part of the rationale of this framework of the standard model extension. You start with a different Lagrangian from which you derive new Feynman rules, and you would have to compute yet again all the processes or particular processes that you may want to have information from, and to answer the question that Roberto was asking, that is one way to do it, to study differences between particles and antiparticles in specific processes, and that's the kind of thing that people working on the SME do. But then again, it's I mean, a lot of work is being done there, because basically one has to reconstruct all the diagrammatica and everything for the specific process that you want to study.
Okay. Yeah. Okay. In this case, it would mean, if I understand, that you have to redefine everything, relaxing some of the constraints coming from CPT or from Lorentz, right? So that's first a huge work, but just not that. I'm not sure you would see effects within uncertainties, right? Because you still have a lot of uncertainties from PDFs. So I don't know if it's a viable way to do that here. I have no idea.
Okay, thanks. So I don't see any further questions. So if that's not the case, let's thank again Aurore for this super nice talk.
Okay, thank you.
And I just want, thanks. I want to remind you guys that we have our next appointment will be next week, Wednesday. Eduardo Peinado is giving a webinar.
Is it next week?
So
it told me it was in 2 weeks.
Week, no? Okay, maybe 2 weeks.
Okay. Just remind him if it's next week.
Please check in the website. Okay, so let's keep tuned, and thank you very much.
Thank you.
Thank you, guys. And then now I have to stop the transmission.
Are we still live?
Yes, hold on.